Hello, everybody, and welcome to chapter number 4. This is Professor Olgara in Thermodynamics. This chapter is named as Energy Analysis of Closed Systems. It's pretty much one of the easiest chapter in the book. It has short information, but an important one that will be served as a baseline for chapter number 5, which is Engineering Devices. Before I start, I want to remember what we learned in chapter number 3, which was related to pure substances. Pretty much we learned how to work with the water tables, how to work with ideal gases, and we learned the equation for ideal gases, and we solved some exercises. I hope you went through previous videos and files in order to fully understand chapter 4. Otherwise, it's going to be a little bit hard. We're going to start this chapter by defining something that is called moving boundary work. One form of mechanical work often encountered in practice is associated with expansion or compression of a gas in a piston cylinder device. During this process, part of the boundary moves back and forth, and therefore, the expansion and compression work is often called boundary work. So how do we start to solve or to see the equations? We know that, regular work is defined as force times displacement, okay? We all know that from physics, and it's the equation that we know. Also, force in thermodynamics is usually associated with the pressure formula, which is force over area. If I solve this equation for F, I will get F is equals to PA. And I'm pretty sure everybody's just familiar with this equation. And I'm gonna call this one number 1. If I put this equation in terms of differentials, then I will get that the differential of the boundary work is equals to force times differential of displacement. And now I'm gonna take this force and substitute it with this one. So I will get something like this. So differential of boundary work will be equal to pressure times area times differential of displacement. So if you take a look at this guy, area times differential of displacement is nothing but a differential of volume. Okay, so if I keep solving this guy, I'm gonna get that differential of boundary work it's equals to pressure differential of volume. And what do I do now? I'm gonna just integrate on both sides from 1 to 2, and then I will get that boundary work it's equals to the integral from 1 to 2 of pressure dV. And this guy right here, it's called boundary work. And that's pretty much what this guy right here, boundary work, is used when we have a piston and cylinder that is going under expansion or compression depending on the case. So I just want to move into the slide. I often, and you should know this by now, I usually just develop the equations and then I show you the slide. So the expansion and compression work in a piston cylinder device is defined by this guy, and therefore we get the same equation I just solved. So what happened with boundary work? Boundary work will be positive for expansion and it will be negative for compression. Okay, we call something that is called a quasi-equilibrium process, and it's a process during which the system remains nearly equilibrium at all times. So if you are compressing or expanding something, it goes so slow that the changes are gonna be almost negligible. Okay, you're gonna hear this quasi-equilibrium process a lot when you're reading the book. So now we're going to get into energy balance Okay, so energy balance for closed systems. And before we get into that, I just want to remember the energy balance for any system or the undergoing any kind of process as we express it. So if you remember, energy in minus energy out, it's equals to the energy or the delta energy of the system. Everybody remember, please, this equation from previous chapter or when we learned the first law of thermodynamics. And there are different, how can I say this? There are different ways of express this whole equation, this very general equation. So we have the first one, the rate form, for example, which is the rate of energy that comes in minus the rate of energy that comes out is pretty much equals to the differential of energy of the system respect with the time, and this is in kilowatts. Okay, we also have another way of express this whole equation as per unit mass, which is equals to energy that comes in minus energy that comes out. It's equals to delta of the energy of the system. And this is in kilojoules per kilograms. Okay, if you remember how we get that, well, pretty simple. Just divide this by the mass, and then you will get the little e. I need you to remember these expressions because we are going to be dealing with these expressions from now until the end of the class, the whole course. Okay, so just remember that. What happened for a closed system? Okay, for a closed system, the initial and final states are identical, and you have to remember that. Okay, what does it mean? Why or how are they going to be identical, and how would that affect my equation? So if you have the first equation which was, energy that comes in minus energy that comes out, it's equals to the delta of the energy of the system. You have to remember that the delta of the energy of the system is nothing more than E at a state 2 minus E at a state 1. If E2 it's equals to E1, this whole thing becomes 0. And therefore I will have that the energy that comes in will be equals to the energy that comes out. And this equation could be expressed in the rate form and also could be expressed per unit mass. Something very important is that this is for a closed system that is going through a cycle, and that means that you start at some point and then it goes through a different path and then comes back to the initial state. That's why energy 1 it's equals to energy 2, and therefore the delta of the energy of the system will be 0. And the real question would be, when do I use per unit mass or the rate form or the general form. That will depend on the data that you have on the exercise. If you have mass and you feel you can do something with that, then you will use that equation. But that's on your, on your own criteria, which one you use. It's basically having a puzzle with hundreds of different pieces, and you need to put them together. And sometimes you don't need the 100 pieces, you probably will need 80 pieces or something like that. So that's why when I'm evaluating my students, I always go by the procedure and not by the result, because there are different ways of getting the same result. So before I move, I want you to know something very important. Okay, you have heat, you also have the rate of heat, and you also have the heat per unit mass. You have work, you have the rate of work, and you have the work per unit mass. This is capital W and this is a small w. You also have energy, you have the rate of energy, and you have energy per unit mass. And this would be more likely as kilojoules. This one will be kilojoules per second, and this one will be kilojoules per kilograms. And always you have to remember the units of whatever you're working with, because then you can play more with the data that you have. Okay, all right, so now we go to specific heats. This part, it's quite important. Hold on one second. Yeah. Okay, so this part is quite important, and I'll tell you why. We use a specific heat when we are working with ideal gases pretty much. If you remember pure substances such as water or refrigerant 134A, previous chapter, so when we had those substances, we will get into the tables with pressure and temperature, and then we will get internal energy, enthalpy. In the future, we'll get entropy as well of those tables. So, but when we have ideal gases, it's a little bit different, and actually, it's a little bit easier, if I'm honest with you. So, let's just define specific heats. They're pretty much amounts of energy required to raise a temperature of ideal masses, but let's just read what it says. So specific heat at a constant volume is the energy required to raise the temperature of the unit mass of a substance by 1 degree as the volume is maintained constant. Okay, and a specific heat at a constant pressure, it's the energy required to raise the temperature of a unit mass of a substance by 1 degree as the pressure is maintained constant. That's why you have P and V. The reality is, why are they important? What do we do with the specific heats and how we calculate a specific heat? So specific heats at a constant volume, they have their own equations. So CV, it's equals to the differential of energy respect to temperature, and CP, it's equals to the differential of enthalpy respect to the temperature. There is a table for CP and CV that we can find at the back of the book along with the water tables, but we're getting into that, okay? Don't worry, just for now, remember this first equation and then the second equation. I'm giving it to you, okay? I'm gonna recall those two equations later. So what happened with them? I mean, why are they important will be the real question. With the specific heats, pretty much I can find internal energy, I can find enthalpy, and I can find a lot of different things. But how so? All right. In order to find internal energy, enthalpy using specific heats, CP and CV. How do I do that? Okay, it's simple. Remember, guys, the two equations I just gave you. CV, it's equals to du dt, and CP, it's equals to dH dt. We're going to use these two equations to develop how to utilize these for enthalpy and internal energy. Remember that enthalpy, it's equals to internal energy plus PV. And also I want you to remember the ideal equation of gases, which is PV, it's equals to RT. I'm gonna take this guy right here and plug it into that equation so I can get that H, it's equals to U plus RT. Okay, save that equation because this is another equation that can be used when treating ideal gases and exercises with that. But the real question would be, how do I get du and dH, or how do I get internal energy and enthalpy for ideal gases using CV and CP? So this is how we use it. I'm gonna take this equation at first, and I'm gonna say that du, it's equals to CV dt. If I integrate on both sides from 1 to 2, then I'm gonna get u2 minus u1, it's equals to the integral of CV dt. And if I do the same thing with the second equation, then I'm getting dH, it's equals to CP dt. And I'm just integrating on both sides as I did in the first case. Now I get H2 minus H1, it's equals to the integral from 1 to 2 CP dt. Okay, and those are the two equations I have. When you move down to heat transfer and move up to heat transfer or thermo 2, you're gonna learn how to get an equation for CV and CP. But now in thermodynamics, it is more convenient to us to find an average value of CV and an average value of CP, so we can keep it constant and then keep working this equation a little bit more. So how do I do that? When you have an exercise, whatever that is, you're gonna have two states, state number 1 and state number 2. Those states are gonna be associated with temperatures. You most likely are gonna be given with temperatures, and if not, you have to look for those temperatures so you can fully develop this equation in order to find internal energy and enthalpy. So, hold on one second. So let me just get rid of these guys for a little bit. Okay, done. So what happened here? If you have T2 and T1 on a state, it is more convenient for you to find a value of CP or CV as a constant. There is a table in the back of the book that give you all the CP and CV with the temperatures in order to find those values. So basically you need to find a T average, which will be equals to T1 plus T2 divided by 2. This will give you a T average or a temperature average. With that temperature, you will get on those tables and you will find CP average or a CV average. If you do that, then you will be able to plug CV and CV into the first two equations I gave you before and get them as a constant. How so? Let me just develop that. We just learned that U2 minus U1, it's equals to the integral from 1 to 2 CV dt. If you find your T average, then you find your CV average, which is a constant, and you can take this one out of the integral and then plug it right here. You will get U2 minus U1, it's equals to CV that multiplies the integral from 1 to 2 dt. And if I keep solving this guy, U2 minus U1 will be equals to CV delta T. And just remember that the CV will be a CV average. And this guy, its equation, I have fully developed in order to find internal energy using CV. Okay, so now how do I do the same thing for enthalpy? So it's exactly the same thing. So for enthalpy, it's pretty much the same case, but now, well, let me just start over. So we have T1 and T2. With this T1 and T2, I'm going to find a T average, which is equals to T1 plus T2 divided by 2. That will give me my T average. With this T average, I'm gonna get into the tables in the back and find CV. I'm sorry, not CV. I'm gonna find CP, which is the one that is related with the enthalpy. So remember the equation, H2 minus H1, it's equals to the integral from 1 to 2 CP dt. Okay, and that's the value you were looking for, an average. So this value now is constant and I can take it out of my integral. And then finally I'm going to get H2 minus H1, it's equals to CP dt. I'm sorry, the integral of dt from 1 to 2. And therefore I get H2 minus H1, it's equals to CP delta T. And you're gonna find these equations in the book, okay? Actually, it's shown as delta H, it's equals to CP delta T, and the first one, delta U, it's equals to CV delta T. These two equations are the most important ones when working with ideal gases. And please remember this, okay? You're going to work with ideal gases in order to use these two equations. You're not going to use those equations when you're working with water. If you're working with water, then you go to the water tables. If you're working with ideal gases, then you need to use these equations. Using these equations is a lot easier than dealing with the tables. So moving along with this. So specific heats, okay, as we were just talking about CV and CP, they're always, important in order to use to develop exercises when we are giving ideal gases. Constant volume and constant pressure, CV and CP values are given for an helium gas right here. And I want you to know something. CV is always less than CP, and the reason why is because when we have a constant volume, the gas is not able to expand, whereas when you have a piston and cylinder, which is not a constant volume but it's a constant pressure, then the gas, it's able to expand, and that will increase the value of CP. That's why CP, it's always greater than CV, and always, guys, remember that. So a little bit, well, I had the true or false, and that could be on the exam. Remember, this is part of the second exam. So is CP greater, it's always greater than CV. I already gave you that answer. Okay, But just remember some facts. So CV and CP are just properties, okay? The specific heats of a substance depend on the state because they're attached to the temperatures, okay? They change with the temperatures, and those temperatures define the state. They are the energy required to raise the temperature of a substance by 1 degree, okay? Is different at different temperatures and pressure. A common unit for a specific heat is kilojoules per kilogram Celsius or kilojoules per kilogram Kelvin. Okay? So always remember that ideal gases will vary. For ideal gases, Cp, U, H, and Cv are always vary with the temperature only. Okay, so you remember that to calculate Cp and Cv, we need to find a T average for both of them. And therefore, once you get that and you get Cp and Cv, you use those for internal energy and this one for enthalpy. All right, so pretty much this is just a resume of what I just developed. I gave you those equations, and then we use these equations as well in order to develop the final one. This one and this one. This is delta U and this is delta H. And this is an integral, sorry for that. But pretty much at the end, what we need to know is that delta U, it's equals to CV, delta T, and delta H, it's equals to CP, delta T. And we use that for ideal gases. So moving. So there are always three ways of calculating delta U and delta H. So by using the tables, U and H, your data available for you, and this is the easiest and most accurate way when the tables are available. By using CV and CP relations, the table that you're looking for is the table A to C as a function of the temperature and performing the integrations. This is very inconvenient for hand calculations, but quite needed for computerized calculations. The results are very accurate. And then we have, by simply using an average of specific heats, okay? Remember that we use a T average. This is very simple and certainly very convenient when property tables are not available. The results are, close to accurate if the temperature interval is not very large. Okay, so pretty much 2 and 1 are the ones that we use for thermodynamics 1. And pretty much, you have the tables when they are open, pretty much water or refrigerant 134A. And then when they're not available, we go and use the equations I just gave you. Just remember that, guys, because I've seen people using the equations when the water tables were open, and that's why they don't reach the right results in the exam or the regular exercise. So when working with ideal gases, this is the one that we need. When working with water or refrigerant 134A, that's the one we're going to be looking for. This part right here, I usually develop that in the class. This is a summer, so we can skip some things, okay? But even though I'm going to skip it, I want to tell you exactly what it is, but I'm not going to include it into the exam, okay? Just pay attention to the explanation, but you don't have to worry about these for calculations or homework because I'm not assigning any exercise related with this. An incompressible substance is a substance whose specific volume or density is constant. Solids and liquids are incompressible substances. So pretty much what happened with this, we're going to develop the similar equations that we developed before, but now CV and CP, they're pretty much equals to C because they're the same thing, okay? As you can read right here, CP and CV values of incompressible substances are identical and they are denoted by C, okay? So how so? So pretty much for liquids and solid or incompressible substances, CP, it's equals to CV, and we're gonna call this just the letter C. So how do I find internal energy? Internal energy, delta U, will be equals or close to a C average that multiplies T2 minus T1. Simple as that, and this is in kilojoules per kilograms. How do I find my C average? Same way, you need to look for T average, and then with that T average, you can get your C. Okay, remember that CP and CB, they no longer exist for this particular case, and they now have become just the letter C. For enthalpy, it's a little bit different. Okay, in this case, I have my equation, which is enthalpy is equals to U plus pressure specific volume. I know that a specific volume is constant. If I put this in terms of derivative, then I have dH is equals to du plus the derivative of the product, which is no more than dH. It's equals to du plus v dp mp dv. We know that v is constant, and therefore that doesn't change. This guy will be 0. And thus I have dH, it's equals to du plus v dp. And I'm going to use this equation. That's my equation for enthalpy using Cp and Cv for incompressible substances. But now I have two equations, okay, or two cases. I have for solids and liquids, okay. So let me just see if I can just for solids, my V delta P, it's 0. Okay, there's no change on those, and therefore delta H becomes close to delta U, which is close to C average that multiplies delta T. Simple. For liquids, I have two cases. First case, when we have constant pressure, and this is pretty much delta H, it's equals to delta U plus B delta P. So this guy becomes 0, and we have the same case that we had over here. Delta H, it's equals to delta U, and this is equals to C average delta T. And then we have another case, which is constant temperature. Delta H is equals to delta U plus V dP, or delta P. Delta U, it's equals to what? C average delta T. So if the temperature is constant, this guy now becomes 0. Therefore, this guy is 0, and at the end I will have delta H is equals to V delta P. And that's the other equations. Like I said, those two equations, I'm just introducing those equations to you in an informative way, and they're not going to be used for exercises in this class. Okay, I just want to be very precise about this. Well, like I'm showing you right now, the internal energy cases right here. Okay, delta U, it's just rewriting what I just wrote. Delta U is equals to the C average, T2 minus T1, and then We have two cases, at a constant pressure, at a constant temperature. There it is. And then if you really want to find the enthalpy at a compressed liquid, you can use this equation as well, which is more accurate than using the one that we learned in the previous chapter. So, like I said, this will not be included in your exams, okay, for this particular course. And with that will be the end of chapter 4. Like I told you at the beginning of the chapter, this is one of the easiest chapter. It's very short. It has compiled information. At the end of the day, what we need to know it's CP, CV, and that with that we can calculate U or H, which is internal energy or enthalpy, and that's useful when tables are not available, or as I always call it, for ideal gases. Just remember that ideal gases, we need to use these relations, and then when we're working with water or refrigerant 134A, then we use the tables. Okay, and then for these we use for ideal gas. So guys, that was all for chapter number 4. I hope to see you in chapter number 5, which is finally engineering devices to get ourselves into more complex processes. If you have any questions, remember that you can email me so we can plan to have meetings individually in order to help you with your doubts. Have a wonderful day. Thank you.